Hello everyone. Today I'm going to present my paper, whose title is A Secure Access and Accountability Framework for Provisioning Services in Named Networks. My name is Nazatul Sultan. I'm working as a research associate at the University of Newcastle and SRDS 61. My other collaborators in this paper are Vijay Varadharajan, Chandan Kumar, Seyit Camtepe, and Surya Nepal. Let me first introduce to you with Indian in a few sentences before going into the details of our proposed scheme. Indian is a new internet architecture designed to cope with the shortcomings of the traditional IP-based networking architecture. It is one of the major architectures of content-centric networking, which idea was coined by pioneer computer scientist Ben Jacobson in 2006. As Indian is a new internet architecture, there are several security challenges that are yet to be explored fully. It is essential to address those security challenges before deploying it in real-world application. Some of the security challenges that we have addressed in this paper are access control, consumer privacy, denial of service attack, ISP accountability, and dispute resolution between ISP and the content producer. In the following slides, I'm going to present a system-level overview of our proposed scheme. Let us assume a very simple Indian architecture. It consists of users, routers like edge routers, internet routers, and data producers like Netflix. Suppose the user 2 wants to access a content XYZ from the data producer abc.com. The user 2 first generates an interest packet that contains the required information about the requested content, including the content name. In our scheme, the user also generates a signature. We design a group-based signature mechanism for that. Once the S router receives both the interest packet and the signature, the S router verifies the signature using the public key of the group, which is publicly available. The S router then forwards the interest packet if and only if the verification is successful. Note that a successful verification implies that the user is authorized to access the requested content. The other edge routers, the other internet routers simply forwards the interest packet to the data producer side. Now we can see that our scheme provides protection against denial of service attack, as the edge routers only allows authorized users to send their request into the network, and it also provides a consumer privacy because we are using a group-based signature mechanism, which doesn't reveal the real identity of the user, nor it allows the edge router or any other entity to link between two subsequent requests from the same user. Once the data producer receives the interest packet, it encrypts the requested content. For that, we design a novel encryption algorithm that is suitable for contents organized in a hierarchical form. For example, in Netflix, the videos can be grouped together based on various parameters like genre, video quality, geographical location, etc. So this group of contents can be organized in a hierarchical form for providing better subscription options to the users. This is a simple content hierarchy of a video streaming services. Normally, a user subscribes for a higher level of content by paying more money can also access the lower level of contents. So once the data producer encrypts the content, it sends the data packets to the user. When an internal router receives the data packets, it keeps copies of the data packets in its cache memory so that if the same user or any other user requests for the same data at a later period of time, the router can satisfy the request without contacting the actual data producer. This reduces content delivery delay. Now, once the user receives the data packets, he can decrypt it if he has proper subscription and associated private keys. That means that only the authorized user can access the contents. Now, in NDN, ISP plays a very critical role actually. As you can see that the NDN routers can satisfy a user's request without contacting the actual data producer. As such, data producers might want to know the exact services provided by the ISP to its users. To achieve that, in our scheme, the ISP collects all the service information, which includes signature of the users, and send it to the data producer. We design a batch verification scheme which enables the data producer to verify those service information. If you can see that there can be a conflict between the ISP and the data producer regarding the service information, and followed by the payment mechanism, because the ISP can take fees from its services to the data producer, and the ISP, either the ISP or the data producer may try to modify the service information for their own benefit. So to resolve such kind of conflict, we design a blockchain and smart contract-based transparent dispute resolution and payment mechanism. In our scheme, the ISP uploads the disputed service information to the smart contract, and the miner verifies those service information in a transparent manner. This is the functionality comparison table of our scheme with some related works. As we can see that our scheme supports all the essential functionalities, including access control over hierarchical content, denial of service attack resistance, authentication, anonymity unlinkability, batch verification, accountability, dispute resolution, and payment mechanism also. We have also implemented our scheme using Mini Engine tool, which is an emulator for NDN. Our NDN network has approximately 40 nodes. We have attached the users to each node and varies it from 1 user to 5 users. The first figure shows the average content delivery, content retrieval delay, where each user requests for the same content. The second figure, in the second figure, each user requests different types of contents. The main goal is to see the difference in average content retrieval delay in these two settings. We can see that the average content retrieval delay in both the scenarios get decreased with the number of users and requests. This is due to the in-network cache property of the NDN, as the nearest routers can satisfy most of the requests. In the single content scenario, it is lesser than the multi-content request scenario, as the content availability will be higher at the routers in the single content request scenario. These are the references. Thank you.